My name is Kuenzer. I'm working for an NEC research lab that is based in Germany. And I'm really glad that I'm here and can present you our open source project called Unikraft, which intends to make building unikernels much easier as before. Before I start, can I briefly ask you guys, just by lifting your hand, who of you heard of unikernels before? Okay. Who of you used unikernels before? Oh, nobody. Oh, that's surprising. And who of you heard about Unikraft already? Okay, one. Good. So I hope the first thing you're going to do is trying it out afterwards, and then it's a yes to all of these 3 questions. So let's start. So you probably have heard that VMs are around since really long time already, and they're really good at enabling you features like consolidation, isolation, and migration. And then this event happened that containers came along and became popular, and people start loving them, and they kind of support the myth that VMs are heavyweight. So, for example, I hear things like containers are much easier to create and deploy. I just write this Docker file and I'm done. Or containers are much smaller than VMs. My VM takes 10 gigabytes, my container only a few hundred megabytes. Or another one is containers are much faster to bring up than my VMs. My VM takes minutes to boot and my container only a second. Where then say, wait a minute, did you hear about unikernels? And don't forget that you get some benefits from VMs like strong isolation, which are harder to achieve with containers, right? Because you have a much bigger interface to the shared Linux kernel than on the hypervisor. So let's have a look on what actually we, as the Unikraft team, understand what a unikernel is, because I also saw that there's quite a bit of different definitions out there. So let's have a look on a traditional VM first. So as simplification, we run one application in one VM, which means we have a standard Linux kernel running there, which is general purpose. It comes with its drivers. These are these colored boxes and subsystem, and we run on a hypervisor, and that runs on our hardware, right? So this is like a simplified software stack of a standard VM. If we take unikernels, what we for sure want to keep is the application that we're operating in there, and we also keep the VM box that we had before. But the difference is that we built a different kernel underneath, meaning this is a specialized kernel that is built only to support your application in there and only to support the target platform you're running on, which means could be either Zen or could be the KVM hypervisor or VMware or Hyper-V or you name it. The unikernel becomes a single monolithic binary which contains your application and the needed or necessary OS layers for it. By saying that we anyway just run a single application in the unikernel, we can also give up the separation within that VM between user space and kernel space, because there's actually nothing else anymore available to attack. So we get a single and flat address space, and we can do just function calls to do our, let's say, I/O with network devices and so forth. And really important for this project is that we can further tweak and tune these OS layers, by changing parameters, swapping out different implementations of TCP/IP stacks and so forth, to get really extreme high performance from this unikernel. So to give you a rough overview of what our previous research was figuring out from this technology, what are the benefits for unikernels. First of all, we can instantiate them extremely fast, destruct them fast, and migrate them fast. And this was all measured in the order of tens of milliseconds. So the minutes are gone. The memory footprint is quite low, so it's usually a few megabytes of RAM. We can achieve with this high density. So in some tests, we got 10,000 virtual machines with Unikernels running on a single hardware. We got really high performance. So these numbers are for one guest CPU. So we built a VNF middle box that could cope with 10 to 40 gigabits of network traffic. And then in comparison, let's say with a standard Nginx setup with a standard Linux kernel underneath, we were 5 to 6 times faster by having a fully specialized software stack for an HTTP server. And then, of course, you have a reduced attack surface because, first of all, you have less components in the Unikernel, and you have the strong isolation provided by the hypervisor. To give you a bit idea in which area we are in terms of instantiation times, I brought you this graph where on the horizontal axis you see how many instances we are creating in parallel on the system, and on the vertical axis we have the instantiation time of that nth service. It's on logarithmic scale. So we take, because this is like research view on this, a baseline process that actually does nothing, just printing out the timestamp when it was up. If we just take the process as it is on a standard Linux system, it takes like 0.7 to 10 milliseconds to create it. If you take that process and put it into a Docker image, we reach times between 150 milliseconds and 550 milliseconds, which is actually quite good. If we take it and take a standard Debian as a VM and create 1,000 of them, that time goes up to 82 seconds. So, and if we go now and look into Unikernels, so we took here a MiniOS. MiniOS is actually was more an educational operating system written by the Zen community to demonstrate how easy it is to write VMs with this parallel virtualized interface they introduced. But anyways, it got quite popular in the Unikernel community. So if we take that, run that same process in there, we get 63 milliseconds to 1.4 seconds for instantiating 1,000 of those. And I can tell you that we have a separate measurement, but I don't have the graph here. If you then further look where the time most is spent on is actually on the hypervisor tool stack, which is figuring out which VM ID can I take, and goes to a linear search in a list that there's no conflict of IDs, which kills your time, and the VM is still not booted. So we were able, with modifying that tool stack, to boot them like 60 of them per second, with a quite stable number independent of how many are in the system. So the application domains for Unikernels as we see, but please correct me with some talks afterwards or give me new ideas. They're kind of coming from these different properties we have. And it's also that each domain may not care about all the properties, maybe just some of them. So give you an example for the fast boot and migration time, which is coming from this minimal software stack. You have the ideas of reactive VNF, so that you boot the network function as soon as your first packet comes into the machine, or serverless. The resource efficiency, also good for serverless, per customer, network functions, IoT, mobile edge computing comes up here. The high performance, which comes from this specialization and tuning of these things. NFV, mobile edge computing, big players in here. And mission critical for things like automotive and IoT. So, this all sounds great, right? And you kind of probably ask yourself now, why is nobody using a Unikernel today? Because, you get similar speed and size as containers, the strong isolation is there, the security is there, but why is not everybody using it? The problem is that these specialized unikernels were so far manual built and optimized manually. So unfortunately, we took that round several times and experienced that building just a single unikernel for a single application takes a month or even longer. And the problem with this specialization is if you go then for application B, you start doing the whole thing again, because that specialization that you did for application A may not fit in a sense for application B again. So that's really not what you want to do, I think, right? So that's why we came up with this Unikraft project, which you could see as a unikernel build framework. So our motivation was that we want to support a wide use case range. So actually, one cares about having a particular scheduler in the unikernel, another cares about a particular network stack, and another one doesn't want to have these features in it to benefit most of the unikernel environment. So that should be possible. These whole building and optimizing steps should be simplified, so users shouldn't care about the code too much. We wanted to create a common and shared code base where all unikernel creators could contribute to, because there's still some overlapping of some pieces of these components which several projects could benefit from each other. So kind of building up this win-win situation. And for sure, also from the beginning, supporting different hypervisors and CPU architectures. And this is how Unikraft got born in our head. We started with the concept that everything is a library, meaning a driver is a library, a scheduler is a library, so even OS functionality is a library. So this involves the task that we need to decompose OS functionality into libraries. And we ended up in having two components then in the end. One is the library pool, and a build tool that brings all the selected libraries then together. So what do I mean exactly with OSD composition? If you look at Linux or any other, let's say, standard kernel that's out there and is really used widely, they're usually quite monolithic, and all the subsystems, or many of these subsystems, are tightly connected to each other, like the memory allocation within the kernel space and the scheduler and so forth. So what we're doing kind of is to find the right split of these components, so that they're getting, first of all, independent of each other as much as they can actually, and once we have that, we have it ready for pick and choose our components to build our unikernel. So in Unikraft terms, this looks like the following. The library pool, which is one of these components, has the differentiation of 3 library types. So we have main libraries, which are actually quite independent of the target platform and architecture. This includes network stacks, file systems, schedulers, then language runtimes, for running C++ programs, for instance, or Go or whatever, memory allocators and drivers. Then we have libraries that we call platform libraries. Those are, in particular, implement as a really specialized version to interact with a specific hypervisor interface. So this means we have a library for running on Zen, we have a library for running on KVM, and actually we have even a library that allows us to run a Linux user space. And then we have architecture libraries, which implement some missing parts that we need for the build for supporting specific CPU features. So there's one for x86, and we have also one now for ARM. So the whole idea is now you pick your application, then you select and configure the libraries that you need to get that working as a unikernel, and the build system is doing the rest. You build it, and then you get a binary image for each platform that you have selected for the build. So to give you another example how this roughly looks like, if you would now build a unikernel that runs a Python program, you would start selecting the libraries like libmicropython, which is a quite lightweight and small Python interpreter, which is originally built for embedded systems. Lightweight IP, also like a lightweight embedded TCP/IP stack. VFSO core for doing some file system I/O, and then here we include this cooperative scheduler, a memory allocator, which is implementing a binary body allocator in this case, KVM platform, and the architecture. And we're done, right? So we have our unikernel that executes our Python program. So the build tool that we built is looks really like Linux, so it was important for us for creating something that especially kernel builders are familiar with. So it's kconfig and makefile based, although there are tons of build systems out there, we still settled on makefile. So you have a make menu config, you choose your options in that menu you want for the application, so meaning selecting the libraries, then you have submenus in there to configure each library there. You choose your architecture and target platforms. So you select, I want to build for ARM, and then you select, I want to have an image for Zen, I want to have an image for KVM, for instance. And then you save your config and type make, and the whole thing is done. You also get a .config file then for your unikernel, so that you can, have somehow saved your configuration. To give you a rough overview, but I really run more over this, what we have already upstream in that project is this set of libraries. You will notice that some of them are quite small, like libukmpi, so UK stands for Unikraft, which is for a message passing interface, so it's a really small library, or libuklog, which just introduces mutexes and semaphores. So the whole idea is also that the system is built in a way that you can come with your own mutex and semaphore library. As long as you follow the API that the previous library had, you can replace the implementations. And that should be possible with all of these items. Because remember, we wanted to say we want to support all of the use cases, meaning there might be someone coming and says the TCP/IP stack that we have there is terrible, that doesn't perform with my application well, so I want to have, let's say, a BSD stack or something. So he can put it as a library and include it in the build and replace the other one. So external libraries, these are libraries that are not in the main tree of Unikraft. Because that repo would just blow up, but still can be just included. So we have there, for instance, a newlib, which is a libc, which is a bit more complete what we have in tree. So in tree we have just a tiny minimal replacement to make really extremely tiny unikernels possible. Lightweight IP as a TCP/IP stack, but we plan actually to port, in fact, a BSD network stack in here to have something that is more feature complete and not focused on embedded systems, and also probably provides us much better performance. Then architecture libraries, we have one for ARM, one for x86, and platforms that we support so far, so please contribute with new platforms, is Zen, KVM, and Linux Userspace. In the pipe, we have currently a preemptive scheduler, round-robin based. Then external libraries are getting more complete, mainly to support more languages that your program is written on, like C++, standard C++ library, or MicroPython. We are getting actually from the ARM people support for the latest ARM v8 CPUs. So they're currently implementing the port for running Zen virtual machine on ARM64. And yeah, also mainly networking is currently going on. To give you some numbers, when we build now here is in this example a Zen unikernel, that actually just boots, says here I am, and then it shuts off, or it shuts down actually. that image is 32.7 kilobytes in size. And for creating that unikernel, we had to actually modify a bit the tool stack to make that happen. So that we can assign 208 kilobytes of RAM, which was the lowest minimum to bring that VM up. It is kind of in the head of the virtual machine or hypervisor builders that 4 megabytes is the lowest limit. So if you put something that is lower than that, you get an error thrown. So we had to remove the check-in really to figure out where's our lower limit of amount of memory that we need to bring up our unikernel environment. So this means when you run the application, then what's added is roughly what your application requires in terms of memory, right? And to give you a bit more realistic example, so we had a unikernel built for NFV, so as a network function, where we used the click software. So that image was 4.5 megabytes in size, and it required 8 megabytes of RAM, and it could cope easily with 10 gigabits of traffic. Yeah, and it's open source. So we actually open source since December 2017. So we started early 2017 internally as an NSC project, and then we decided we go as early as possible public. And we had some relationship with the Zen project and collaborations before. So we had discussions and ideas and exchanges with the Zen community until we decided then, yeah, let's go there and make it public with them. So we became an incubator project of the Zen project, which is also then on the other hand covered by the Linux Foundation. The community is also growing. So over the year we got several contributions, like from Romania. There were some students working on networking and scheduling mainly. From Israel, we got support for bare metal, so we could boot it on a x86 bare metal mode. A VGA driver was implemented. And then from China, this is actually mainly the ARM folks. They provided us the ARM V8 64-bit support for KVM, and they're currently working on the Zen port. But as you see, there's still a lot to do, so I really hope you get in touch with us. And actually, it doesn't matter if you want to be a contributor or you just want to use the system or you want to integrate it in an architect, or maybe you want to build a POC, right, to just test the technology with it. It's always good for us, at least, to get early in touch, because that also gives us the possibility to learn about what your use case is, and we could maybe accelerate steering it into your direction earlier, but also to make the API design between the libraries correct early on. So yeah, so please talk with me and get a sticker. Here I give you again an overview of the resources, but you will anyway have afterwards the access to the slides, I hope, right? So it's also noted here so that when you open the slide set, you have all the references you need. So thank you. So I'm open for questions.
Thank you. Very cool talk. 2 questions. One, how reproducible are unikernels? Like the Debian reproducible builds project and various other things are looking at, can you guarantee byte for byte reproducibility with 2 different builds? And the second question is,
wait, can you repeat the first one, because
sorry,
a bit of echo. I didn't.
Are unikernel builds with Unikraft reproducible? So if I set up a config file and I run the same build twice, will I get byte for byte identical output or not? Yes,
because you give the configuration of the libraries, it's exactly identical. Of course, what you probably will start doing is, like, maybe measuring if your performance is kept. And if you're a bit more into the system, you will start playing around, changing some parameters, recompile it, but actually every change of a parameter is a new config file, right?
Yeah, but okay, cool. And the other question is, from a manageability, operability point of view, like, you've just got this one binary artifact, right? So if you want to change a flag or a parameter in, like, your Userspace binary, that's effectively a full rebuild, right? There isn't a concept of pushing config to a running unikernel instance, or am I misunderstanding?
For now, that would mean that, except that, let's say, it depends also a bit how you build your application. And also we have one library that is taking care of your whole bootstrapping process. So as I said, you can replace every library to fit into your use case. And really talking about here, since I come with a NFV background here, you really want to have full control which thread is started where and when is a network device initialized and so forth. You can implement parts of the system by yourself by replacing a library like the bootstrapping. And nobody is stopping you in, first of all, parsing command line arguments of the kernel, or loading a config file, or adding a system that you have, like that a config file is loaded maybe from the init RAM FS or something like that, so that you make it more configurable. And for sure, if you now build a Unikernels to support like a high-level language like Python or whatever, you probably want to have somewhere an option that you put your Python files in something that is not part of the kernel binary, right? And get configurability like this.
Thank you.
Thanks, that was a great talk. So I'm wondering, is it realistic to port an existing Linux application to a unikernel, or are the libraries I'm going to wind up with so different from what I started with that I've really got to start all over with my application?
So actually what looks different are the decomposed OS libraries, how we implement the operating system features, what you get from a standard Linux kernel. But on top of there, we try to get, let's say, OpenSSL, standard libcs like Muscle, newlib, and so forth, so that is completely the same for your application interface in the end.
Okay, and in terms of selecting the operating system components, do you have anything to automatically compute that? Or if I guess wrong, do I just get a link error? Or how does that work?
So what you have is with this kconfig from Linux, what we use there is like defining dependencies. For instance, if you say include a new lib as a libc and say I want to have here the file system open, close, and system available, it will then automatically select the libraries of the base OS components so that the build actually happens. It shouldn't happen that you could end up in a configuration that you end up with a compile error. So you really, each library has dependencies defined so that at least that build is safe.
Thanks.
Well, I guess it comes down to building an application dependency model to understand which modules to actually include in the build.
Yes.
And that would be actually a big question mark in a sense of how would you know if you have a Java application that you want a unikernel, what kind of binaries, what kind of dependency model would you explore in order to actually pick the right recipe?
That's actually a good question. This is also something we're looking at. For now, we are really busy providing you a base to kind of complete POSIX compliance. But for sure, this is something we are going to look at. So this is a really good question. For now, you have some pre-knowledge, right? You know it's a Java application. You know you need a JVM, and hopefully it's there until that point already, so that you can just select, I want to build a JVM and get a JVM unikernel. But you introduce pre-knowledge for now. Right?
Yeah, exactly. And I think that's a big question mark.
Yes, exactly. I agree, and we have it on our agenda to how you could automate that further. But that didn't happen so far because we're still busy. We don't have file system support yet. So this is, really essential pieces are still missing.
And another front is the unikernel. What does the unikernel sell itself? Is it security? Is it optimization in terms of speed, performance? Memory footprint, because the way I see it, it's literally only for security, right? You have a small footprint, maybe you sort of cover down the security better, but performance, I mean, the kernel is already light as it is. If you do take out 50% of those modules, will that really impact?
Especially if you specialize the components in your full stack, right? Because usually when you run on a standard kernel, you can only performance optimize your application there, and at your kernel API, you stop. Or if you go further advanced, you start introducing features like SSL offloading features to the kernel, right, to cope with really high rates. Here you have a single monolithic system where you can do whatever you wanted. You don't need to care about general purpose compatibility because you build it just for that application. So it's much more likely that you go into the OS components and start changing them there. And I can just tell you from our past experience building an HTTP cache node, specialized from the file system that we wrote from scratch, the HTTP server that we wrote from scratch, plus you know, even tuning and changing the implementation of the TCP/IP stack. We got much better, or let's say impressive performance compared to standard Nginx running on a general purpose kernel. So there is quite a potential actually.
And it's also good to provide some kind of color in terms of what is the difference between running an application in a container, running a unikernel, running it as native. Is the throughput increase? Did the latency decrease? What's the percentages?
So we saw in our, maybe I refer you to some papers maybe later after the talk. Okay. For sure, lower latency is one fact because you can reduce your whole call stack for networking. Throughput you can increase because processing a request you can do much quicker than doing a system call for just finding the file, the next system call for opening the file, and then building up the request and so forth. You can bind and couple these components much closer together. So performance, and this is actually where we come from with this NFV background, was really a key important factor for us. And it is possible. The other thing that you get extra is the VM isolation, which they're really good at with the hypervisor interface, where you actually get the security just because you can define by attaching virtual devices or removing them. You kind of have the ability to define your interface to the hypervisor. Yeah, right, and the Linux kernel is like you have your 650 or whatever system calls. Of course, they're also working on the security. So I'm really not against container or whatever. But it's much harder to achieve, right? To get a full coverage and also components removed or invisible or non-reachable of a general purpose kernel. Awesome. But also the task of a general purpose kernel is a different one, right?
Awesome, thank you. Sorry.
My question is regarding observability. If some third party builds a unikernel and ships it to me, and it performs pathologically in my environment, how do I find out what it's doing? I can't run my usual ftrace, strace,
yes, of
perf.
Course. Yeah, this is true. Probably in that case, either you use the monitoring tools of your hypervisor environment, what you ever have from the outside, or it's a requirement in your case to include a special maintenance library that gives you an entry point for that. So that would be how you would approach it.
So I need to know upfront what's going to go wrong later.
Yeah.
Not my experience.
No, I mean, if you could go and say include a shell. Right, include a shell with a set of commands to analyze what's the status of memory allocations, what is the TCP/IP stack doing, and so forth. Nobody's stopping you to do that, right? It's that system shouldn't stop you building such unikernels, if that helps. Right, of course, yeah. I got this question also before. It's a good one. Thanks. So get your stickers.